Wow, last session of NDC. How you guys? Have you been having fun today? Was it? Anyone learned anything new? Very good. Right. So how many people here, because there are only about, how many people here have actually written an interactive application before? Something that involved actually having input coming from a user, doing stuff with it and all that. Anyone? Business application? Any kind of business application? Cool. Right, so I'm speaking to the choir. Everybody understands what I'm going to talk now. That's good. So what I'm going to do is I'm going to take a little business application and I'm going to dissect it and put it back together. And then maybe it'll be better than when we started with it. And hopefully along the way we'll talk about what we did, some principles and so on, and see if we can learn something new. So in my past life, hang on, let me just figure out what to do here. Right. So in my past life, I used to be a consultant. Anyone seen what a blobber is? Does anyone know what a blobber is? Yeah. So Scott Lashin, one of my friends, he's in the room over there doing his own talk, calls boring line of business applications, right? And usually it's something like order processing or insurance claims management or leave application tracking or something like that. And customers who come to me and want one of these things done. And most of these line of business applications, they're obviously very interactive. They tend to want to process, some thousand of these, in some time period, right? Tax returns, so many thousand tax returns a year, or so many invoices a month, or something like that, right? So there's usually some element of scale associated with it that you have to design the thing for. And then there's the concept of a business rule, which is kind of specified in terms of everyday life. Because, the people have been doing insurance, 300 or 400 years or something, before computers anyway. And so they want to apply the same business rules in the computer process. So even if you go and try to get admitted in hospital, they want you to fill out a form that looks very much like the paper form that they used to fill out 50 years ago, right? And so the business logic is sort of very domain specific, and people basically want to keep the existing one, so they tend to be a bit complex. And you don't necessarily fully understand the complexity of the domain. So the requirements are usually presented to you progressively. Now, to make things worse, I was actually a consultant with a development team overseas. So they definitely give everything to you piecemeal, right? So you can't understand the whole system up front. You can't design everything up front. You've got to spend a fair bit of time building something that they need right now, but leave yourself enough wiggle room in order to be able to accommodate change later. We're definitely not writing fire and forget kind of things. Now, usually when you have this kind of a system, what ends up happening is that the systems architects, the big guys, they go off and they talk about scale. And they talk about should we design for the cloud, and what kind of clusters do we need, and how much memory, and what kind of databases should we use, what's our failover strategy, and this and that. And most of it centers around some very interesting problems, and most of it centers around spending money. So you buy a new kit and you do all kinds of cool stuff. The capability side, that's most of us, developers and applications engineers who try and design the system in such a way that it meets all the requirements that the customer needs. And does so in a way that gives us, as I said earlier, wiggle room. So we bring craftsmanship into it, we bring rules of experience, we bring, best of breed technologies, whatever it is. We look at new stuff that's happening, but most of it is really, I've done this before, it doesn't work, we have to do it this way. And that's the learning process that we all, get in conferences like this. You guys can relate to what I'm saying, right? Cool. So at some point, we actually finish this thing off. It's a good thing. We apply TDD and BDD, we do all the domain design and all of that, bring the whole thing, get it up and running, have a shipping party, right? Consultants get sent home. Everybody in the team moves on to something new, and then thing goes into production. And there's some team in there who has a vague relationship with the team that wrote the stuff in the first place. And some change request comes in. And that's when everything starts falling apart, right? And I think the reality that we have to understand is that things starting to fall apart is not necessarily a function of bad coding practices or anything like that in the first place. You cannot build something and make it future-proof, perfect today. It's just not possible to do that. And the reason for that is simply because of this. We have human communication. That's the problem. Somebody has to communicate the specs to us. That's laden with ambiguity. Then somebody writes some code that's dependent on the specs, and that's an interpretive function of understanding the spec. So the person now who's reading the code has to deduce intent, has to deduce context, right? Has to figure out what the breadcrumbs are so that they can do this thing, make a change. And then once they make the change, they've got to leave breadcrumbs for the next person that comes along, and there's a new mystery that needs to be solved, 6 months down the line, why this line of code is here. Did the developer do something clever? Did he understand something more about the nuances of the system that he put this code in? Or did he just not get it, and did he introduce a bug? I mean, we don't know just by looking at it. So the only hope for actually doing anything at all must be to try and communicate better. And that is, you've got to make stuff declare intent and formalism as early in the process as possible. Now, we've started with the whole, let's not have a spec written in Word, let's write BDD and do stuff, because then the spec becomes a live kind of document. And that's a good thing. But that doesn't really inform us about the quality of the code and how the code is actually going to degenerate over time. Because when someone makes a change, they're not necessarily communicating everything they can with the change. And comments don't really help. Let's be fair about that, right? So what does better really look like? We want to write systems that make it easier to reason about the application that we're building, reason about what we're trying to do. And then, when you make a change, the approach that you take and the code that you have and the platform that you've built this thing on, better make sure that this change is done safely. So you don't introduce unnecessary side effects into the system. The third one's the most contentious. It should not involve a wholesale change on what you're doing right now. So this isn't a talk about where I say you should start programming Haskell. You should, but not because of this. Or F#. You should, not because of this, right? The need for the change is not specific. You won't get the benefits that you want just by changing wholesale everything that you do. So what we need to do is find a way to communicate intent and raise the level of clarity of what we want to do. And that's kind of the background for where we are right now, what I want to do. So with that in mind, let's build a bank, right? I have only 3 business rules. I'm putting on my customer hat. Only 3 business rules, right? A bank account should have an initial balance of 0. It can support deposits of money without limit. When you deposit a certain amount, your balance will be increased by that amount. If the balance is positive, then I'll support withdrawal, and you can take some money out, and the balance will be decreased by the amount that you take. I don't think requirements get any simpler than that. Does anyone have a semantic problem with those rules? No? Okay. So how do we build an application that would do this? Now, I don't know if any of you came to the talk we did at 3 o'clock on Orleans, and we talked about the difference between stateful and stateless and so on and so forth. So I'm just going to assume that you're dealing with the standard best-of-breed technology today, and we're going to go with, building a service-oriented thing or something. So we'll build a bank account service. Sounds reasonable? Yeah? So I have a bank account service. This is what my first rule looks like. When I initialize my bank account, that has a balance of 0, and I've got to save it somewhere. So in a standard SOA kind of thing, this sounds reasonable. Anyone have very fundamental problems with this? No? Cool. Deposit? Reasonable? Shout out if anything is unreasonable, right? So we have this concept of this. Now, let's say we've not just written this bare service, right? We've got TDD in place, we've got mocking, we've tested the crap out of this thing. We can do what we want to make sure that this thing is running production stable. But we've had the party, people have gone home, right? And some junior guy is now taking over the maintenance of this thing. And the first change request comes in. I want to support closing a bank account. And here, again, 2 simple rules. A closed bank account shouldn't allow you to do anything on it. And a bank account requires a 0 balance before you should close it. So just simple rules. Now, we're an agile shop, right? So somebody actually puts this card out. Then there's a team that sits down and figures out what you need to do in order to make this thing happen. Again, shout if anything here is unreasonable, right? You've got to create a property, you've got to modify all the existing code to the test to make sure that the existing tests are talking about closed bank, no, non-closed bank accounts. Then you write new tests for the bank accounts that are going to be closed, ensure that they don't accept deposit and withdrawal, right? Modify the service code, and then add a test to verify close. Then write the code, right? Any of this? Have I forgotten something? It looks good. It's a fair bit of work, but it's there, right? I've captured everything. Initialize. What happens if I bring a bank account in and it turns out to be, if it turns out to exist, but it's closed already? Now, a normal person would not have asked that question, but somebody who's skilled at maintaining this code would realize, hey, this change is coming in. This is likely to come down the pike sometime soon. So let me, while I'm looking at the code, put a flag in here saying something else. We may have to look at something. And the BA, of course, junior guy, looks at the spec and says, the spec clearly says that a closed account should not allow anything, right? No reactivation. The crusty old beard like me will turn around and say, okay, that may change. We'll see what happens. So then we say, okay, if the bank account is closed, make sure that we don't proceed further. And we do that for deposit and withdraw. And then we write code. What happens if you try to close a closed bank account? Well, somebody says it should be a no-op. Should we implement a no-op by returning, or should we implement a no-op by just following all the way through? I'm belaboring this point to show you that a reasonable set of rules that was very simple and clear to understand leads to ambiguity with the best intentions in play. And this is the state of reality. Now think about this when you don't have everything in together. And you can see how everything is going to just, the entropy is just going to enter the system and systems are going to fall apart. So, where's all the pain coming from? I would suggest that the first source of pain is because we started by trying to deal with scale in the first place. So in our previous talk at 3 o'clock, we talked about how when we were all babes in arms in CS 101, we landed up going to school and they gave us this OO manual and they said everything's going to be golden from now on. We got encapsulation, we got abstraction, data hiding, inheritance, and all of that lot. And so we started writing code that embodied all those principles. We had controlled access to make changes. We had full control of the object, the data in place, what operations are supported, and everything was self-contained. And then we went to run it on 2 machines. And all of a sudden, you had to go stateless. So you put the guts of the thing, the data in the object, in some separate store, have multiple services that stood in the front of the thing, and now the logic lives in the service, the data lives somewhere else. You call it separation of concerns, everyone's happy, people write books, and all of that. But in reality, what's happened is you've invited a whole bunch of really dangerous people to your party. And now you're trying to figure out strategies on how to deal with those people, right? So we gave up controlled access, and we got concurrency headaches. So now we've got, optimistic locking and all the other jazz that comes with that. We gave away abstractions so we could get scale. And we gave away abstraction by taking out all the logic and putting it somewhere else. And then we have the elegance of just doing the object-orientedness of it. And we put in an ORM. The ORM's got leaky abstractions everywhere along the line. It's not really an object. You still have to deal with this idea of persistence and all this other garbage that goes with it. So we have some major issues. So let's look through the world through slightly different lenses at the moment, right? If I wrote the thing as an object, that's what it will look like. It's got a bank account ID, a balance, a constructor, a private property tells you if it's closed or not, methods to do deposit, withdraw, and close, and just to be correct, I opened out what withdraw looks like. And that's kind of exactly what you do. Everything's self-contained. You can't mutate balance without going through one of these things, right? You have a hell of a lot more control over what's going on. And it's not likely that the thing is going to go out of hand easily. Everything, all the changes are in one place. But I'm actually not... and the service for this would look like this. Notice that all it's doing is calling deposit on the object itself. And now immediately we've done 2 things. We've taken away the repository business. This account does not exist business, or the account exists already, is not really a concern of the object itself. It's a concern of your storage. This is part of the leaky abstraction that's coming in. Why should the bank account be worried about whether it exists somewhere else? That's some representation of the storage that's the problem here, right? So by separating this thing out, we've already said that we're going to push all of the storage-related stuff out a little bit and try and contain the business logic-y side of it into the object. Everyone with me so far? You guys probably already do this, right? So none of this may be new. But I want to point out these 2 pieces in here. I think this is the place in Denmark where it smells. There's a red bit and a green bit. Can anyone... So from what I've heard, most people will be comfortable with this code, by the way, and that's perfectly all right. I'm only trying to be a little bit more nitpicky on it. I think that the red bit has something to do with the structure of the object and its behavior, and the green bit is about its performance, its capability, what it's actually doing to the data that it's holding. And I think those are 2 actually separate concerns. They're not the same thing. But given the way in which we've built our object structure and the languages that we use, we can't really separate those 2. I want to introduce 2 kind of biggish words, the $64 words, the affordance and the capability. These are actually representations of the 2 things. The affordance is what an object allows you to do to it. And the capability is what the object does to, what the object itself does. And separating those 2 out, I think, goes a long way towards helping us understand what the system does a little bit better, right? So let's rewrite the thing as a table, and you can see that there's a form of the object that is in 0 balance. When it's in 0 balance, I can close the account, at which point the balance stays unchanged. If I deposit into a zero balance, it goes into a positive balance state, and I increase the balance. And those are two different things. Those are actually two different things. So if I do this and I try to map out the affordance of it and the capability of it, the first thing that leaps out is that you're not writing one class. You're actually writing a separate class for each of the forms of the system. But you've only got the one object. So how do you separate the things out and make it so that the object shape-shifts itself into the shape that you want? So I'm just going to put this there. I've taken the table, and I've just made it look like a little different, right? Does anyone have a problem with the last four sections? Can anyone tell me that those last four sections are different from the table? They're not. They're actually the same. I've just re-implemented this piece with curly braces. Okay? In the meanwhile, I'm going to take a short digression. Now, I happen to be a big fan of F#, and we have a way of modeling choices. So in the world, the F# and the Haskell and the Scala world, there's a special kind of type that allows you to model choices. And those types are difficult to do in languages like C# and Java. You can do them. They take a lot of effort, and there's a lot of work that you need to put in place to make that work properly. And there's a reason why we need these, because if you look at the set of things that we want to deal with, if you look at the bank account object itself, it's really one of four different types, as we just pointed out. The four independent little pieces of little shapes of that object. And in some sense, you can model that using union types. They're called union types or choice types, right? We also have a restriction kind of situation. Now, most of you, anyone here, have you used Java? Okay, so you know the extends keyword explicitly says that a derived class is the base class plus something. The C# guys just use colon, and that meaning is kind of lost, right? And extension by inheritance is a traditional object-oriented concept. We need to understand that well, right? But with union types, you can actually restrict a type as a subset of another type. So if I have three choices, red, amber, and green, I can say that the two colors that represent when I have to actually break and stop are red and amber. I can actually make that modeling choice. So you need restriction types and union types. And the announcement I have is that you can now do this in C#. We actually have the ability to do this. This is not an official C# release yet. But it's an open source project that I've basically worked on, and you can now start writing stuff like that. Now, with the end of that digression, we can go back to this and look at it as a set of choices. If you look at the message, a message is either a deposit message, a withdrawal message, or a close message. We know this. Similarly, the set of states is a set of choices. The set of events, the set of messages handled in each state is again a choice type. The set of valid return values is also a choice type. And so by looking at this from a type-driven perspective, we can actually generate the various shapes of the object and put it all together. And we do that by basically building the class hierarchy in C# that looks like that using a tool. Because writing all of this stuff by hand is actually where a good bit of pain comes from. If you look at the kind of work that you would normally have to do in a traditional web application, a good amount of work that you're doing is actually hand-rolling this logic implicitly into the code, and I'm trying to get it out. So we can make it as general as possible, and you can write, say, for example, the shape of an active message handler only handles deposit and withdrawal, and it has special types for its result. And we can generate all of that for you. And I'll show you how it's done, but let's just move on in a moment. How you inject the capability, though, is exactly like this. If you think of the active deposit result as an enum of some sort, you can tell that it's actually it has only one element in it, which is active. And depositing money into an active account can only leave it in an active state. So the whole idea of you having to cut and copy and move things around and leave an unfortunate state transition somewhere in your code is completely eliminated by using this approach. And that means also that you don't have to write a test to ever say, I'm in an active state, I can never get to a closed state. Because there's actually no way of representing the fact that this withdrawal function ever puts you in a state where you are closed. So giving you the type safety goes one step further in making sure that the changes that you are about to make are going to be safe and supported. So what have we done? We've kind of dissected the system, and by a little bit of sleight of hand and hand-waving, I've told you that we can declaratively specify a state machine. Right? May not be worth anything right now, but just take my word for it for the next 2 minutes. From that state machine, I can automatically derive the types that enforce the safety of the code that it generates and the safety of the code that you will have to write in order to make that work. And doing that has removed a great deal of handwritten boilerplate logic that you would have to do to handle the if cases. You know, the red bits that I showed you earlier, all of those are taken out of the equation. You've removed entire classes of tests by ensuring that transitions that cannot happen cannot be represented. And then by decoupling the capability and affordance, you're only limited to handwriting the capability piece. The affordance part of it, the shape-shifting aspect of the solution, is actually taken care of by the compiler of this new language. And of course, once we're done with that, we can actually take a look at the FSM and realize that it's just a representation that we can analyze by ourselves. So for example, we can say, hey, by looking at this state machine, you are never going to get to that state. It may have handlers in it, but it's no longer needed in the code. So how many people have looked at existing code and wonder whether the function is actually being used anywhere? Or whether we are capable of just blindly removing this block of code because it doesn't seem to be hit anywhere and tests don't fail because I can remove it, and then it goes boom in production because somebody still got some old version of the thing that runs and puts it in an illegal state. This will remove entire classes of that kind of analysis and make it easy for you to reason about the changing shape of your object because you've declaratively put it somewhere where someone can reason about it. Also, infinite loops. When I receive this message and it goes into that state moves to another state and another state and another state, and then the only way to get back is to go back into this. So you're now stuck in a loop that's got 5 or 6 messages in there. You can't look at that by looking at code and deducing that easily. It's just not possible to do that. You can't expect somebody to do that. And so you come up with novel ways of actually testing the thing and doing all of that. All of it is complete nonsense because you can evaluate the shape of these states well before you even generate code for it to tell you whether you're going to have a system that will have an infinite loop in it. So by doing all of this, we're actually, and the last one is most important, is we guarantee that if you change the set of something, it changes a type which means something is going to break in compile time, which means you have to deliberately go and look at the impact of your change in the code before you can actually ship it again, which means that you can write code with some level of certainty that a change that you made to the behavior of something was dealt with deliberately as you went through the whole development process. So the cost of doing this, of course, was that we had to write our own language to do it, right? Very simple. I'm going to dive into Orleans now, but does anyone have any questions so far? Is anyone still awake? Excellent. All right. So let me outline Orleans in a slide, and my co-presenter, Sergey, here will probably look at it and wonder if he wants to talk to me again. So basically, to put it in very succinct terms, Orleans is object orientation across machine boundaries. In object orientation, you have an object, you deal with it through a reference. The reference happens to be an address in memory. In Orleans, you deal with an object through a reference. It happens to be hidden from you. You deal with the reference in memory. That object could be anywhere in the cluster. But the programming model is literally it's that simple. And that's really what I want to leave you with. This is the salient part of it. It's basically a traditional programming paradigm. You call messages on it. Everything's built in with asynchrony because distribution involves asynchrony. We embrace that right from the start, right? Orleans will take care of your object. So think of it as garbage collection in the cloud. It's got that. And the one thing that's very interesting is that Orleans will guarantee single-threaded access to members of its object. So you don't have any concurrency headaches. So you just remove the entire concurrency problem. Declarative persistence allows you to save the object state in the cloud, on the disk, whatever storage platform you want. So it's entirely possible for you to write this thing and deal with it, at terabyte scale without having to leave the principles of object orientation that you learned in CS 101. I think that's a very compelling proposition, but I'm about to make it even more compelling at this point. Anyway, when you can run at scale, and then we write in idiomatic C#. So it's all familiar stuff. No one's asking you to do anything funky. If you want to do it in F#, you can. You don't have to at all. You can do all of this stuff in C#. What we do is we take this FSM and generate the code for writing an Orleans grain that has the shape-shifting behavior that I pointed out earlier built into it. And that's what I'm going to show you right now. Right. So let me see. I'm going to see if I can do this. Ooh, that's too small. Yell when it's big enough. Can people see that? All right. So the first point of call is, oh God, don't tell me. Is the Visual Studio Marketplace. This tool already exists. It's up in the Visual Studio Marketplace. If you've got Visual Studio 2015, you can download the tool. It's in version 0.8 at the moment, but it'll get improved. The code's in GitHub, and I'm not connected. Brilliant. That's the code in GitHub. I'll give you all these links, but basically that's what it is. And the C# union type stuff is there as well, as I mentioned earlier. So what we'll do is we'll fire up Visual Studio. Sorry. Can everyone see that, or do you want me to zoom in further? Cool. So here's our bank account, which we knew about before. What have we specified? We specified that it has an identifier. So this is the object's handle that we're talking about, right? We're going to operate on the balance. We're going to process these messages. It's initially in that state. These are the 4 states that it can be in. The handlers for each of those. So I'm going to take the, close your eyes for a second. And there's a custom tool that comes when you install the V6. And you install the NuGet package to get this reference. And we'll just save this file. And lo and behold, the code associated with each of the states and the union types and all of that is written in code that you can actually debug. So you can put a debugger in this if you like to figure out what the heck is going on at some point in time, right? And I would assume that by the time you get to the point where you say it's 506 lines of code, and if you try to look at what's actually being done, it's a fairly complex piece of work, but you didn't have to do any of it. And the net of that is that you can generate a partial class, and it'll tell you, hey, I've done all of the hard work for you. Please. Oh God, what have I done here? What am I going to do here? I should have bought a mouse. And it tells you that in the overdrawn state, I can only do a deposit. And if I try to return anything other than something from overdrawn deposit result, sorry. Yeah, I'm just going to look at this. I'm showing you this enum. The overdrawn state basically allows you to go from an overdrawn state to an active state or a zero balance state. It does not let you go to closed, which is the rule that we said earlier. When we handle an overdrawn message, the only thing I should be able to do is put a deposit on it. And depending on how much I deposit, I should be able to either stay overdrawn if I didn't put enough money, or go to zero if I put in exactly how much I owed, or go to a positive state if I put in more. So it's not even possible for me to write a state here that's by mistake closes the account. And the reason why this is possible is because of that whole restriction type thing. Because at the end of the day, the state machine message handler still has to return a state, a real state. But I need a subset of the set of states for this specific purpose. And that's kind of where the restriction types come in. If you didn't have restriction types, you could not make this strong guarantee that you can, if it was just an enum and you return something, you could potentially return anything you wanted. It's because this is a restricted type that you're able to make the strong guarantee that the transitions are all well understood right from the start. Right? Anyway, so here's an example of the union in place. And to give you an idea of what it takes to implement a union, that's what it takes to implement a union. So there is a reason why nobody writes union types in C#, because for a single item union, it takes 45 lines of code. And most of it's boilerplate, and it will get pretty old pretty fast. And you'll probably cut and paste stuff, and it'll be wrong and make mistakes. But a compiler like this can actually do the work. Now, if I went in and actually read the business logic, we could make sure that this thing could actually be testable and run. Also, the individual functions here are actually so well constrained that you almost never have to mock anything. There's nothing to mock it, say, put the bank account in the overdrawn state, and then try to make this this change to see what happens. You already put in a condition, in a conditional state, where a simple unit test will suffice. So by using an advanced technique like using DSLs to do this stuff, we can actually make things much, much more efficient and much, much safer, right? Now, I'm actually done with the Orleans part of it and with the state machines part of it. I anticipate a bunch of questions, and if there's anyone who's really interested in figuring out how the stuff works, I'm happy to show you that as well. So it's over to you guys. Any questions from anyone on anything? So, okay, so basically there's a concept of an algebraic data type, okay? And an algebraic data type basically is a way of building bigger types from smaller types. There are two ways of doing it. As C# people, we only know of one way, which is we create a class or a struct that has a bunch of properties. And if you think about it, the cardinality of that set is actually the product of the cardinality of each of the members. So those things are called product types. Union types are the dual of that. They are the sum. And as far as I'm aware, C# doesn't have in its roadmap a way of putting union types in there. But if you have sum types and union types, together you can build up a type algebra that's actually pretty expressive, and you can actually restrict a lot of issues. You can make, as Scott Lashin puts it, you can make illegal states unrepresentable, which is kind of the example that I have here. It's not possible to actually model a failure case and make the thing compile. It's not possible to actually get into that state. So in terms of the relationship, C# itself doesn't have union types yet. This is a Visual Studio tool, so you can actually run it with Visual Studio if you want. There is also a command line tool in the V6 package that allows you to basically the NuGet package, that allows you to run against the FSM file manually and generate the code. So you don't need Visual Studio to run with this. It's just that it's very convenient because every time you make a change, the Visual Studio engine will kick in and actually generate the code for you, right? But it's basically written in such a way that you can pretty much run anywhere, including Mono and stuff. We have a build pipeline running on Mono at the moment. So, any other questions? Okay, does anyone want to know how this works? You want to see so the secret behind this is actually a whole ton of F#. So I'm probably going to lose a whole bunch of people. Maybe I'll end the talk here because they're videoing it, and then we can show the code later. Or would everyone want to see the tool? Does everyone want to see it? Okay. Okay, let me finish the presentation and with this formal acknowledgement. So So I have to acknowledge a lot of people who have helped me to get this across the line. Scott Lashin, of course, is a huge influence on a whole bunch of things. I have colleagues, Ivan Tolson, Mark, and George, who basically helped me with FParsec and getting the rest of it going. Sergey, of course, been an invaluable resource as far as the Orleans side of it goes. And I work for Microsoft, and they've graciously let me actually present here. So I'm actually presenting on behalf of Microsoft. So thank you to them. And those are the links if anyone wants them. And I'll make them available to you later as well. We've just hit 50 minutes, right? So I've got 5 minutes now, so cool. Let me just fire this thing up locally. So the actual work required to create the DSL and to parse it is actually very, very small indeed. I want to get rid of this thing. So this is the language representation internally, where I have identifiers and data type names and elements and blocks and messages and so on and so forth. And I built that using a parser, which is literally 50 lines of code that actually walks through the text and parses the elements out into the object. And then I analyze the validity of the thing, because you don't want to have transitions to states that don't exist and so on. It will generate code that doesn't compile. And the state machine itself has these properties, as you can tell. This is how I build up the various type names and so on. Because I use union types, I can actually directly use the class declaration of the union type itself. I'm just using the union type as a library. And this generates the code. So here's actually the constructor of the grain state class that gets injected into the thing. So if you look at the grain state class, which was I shouldn't have closed the other one. But if you look at the grain state class, this actually generates the Orleans bit. Basically says that it needs a grain state, it needs a grain interface, and so on and so forth. And each of those things, so the grain interface, which basically looks at the various methods, is actually this piece of code. So if each piece of the code generation doesn't look like much, and that's one of the beauties of using F# for this, because it's very succinct, and you can actually, all these funny looking things that you see here are actually Roslyn calls. And you don't recognize it as Roslyn because I've hidden all the ugliness away and do something that makes it look like something that it actually will generate. So for example, in this case, I generate an arrow method that calls through and has the type of task of the data type name, which if you remember the code that I wrote, is exactly what was generated out. And so there's more of that, and we eventually just generate code using Roslyn. That's kind of how it works. Further questions? Confused everybody? Well, Mark Simon's looking very pleased, so I'm happy. Yeah? Matthias, you asked?
How would this play out with the F# discriminated unions and so on? Like, could you map out like what you're generating, which is so you're essentially emulating a DU on the C# side?
Correct. I've dispensed with the pleasantry of making F# being able to call that DU natively. So the C# one is actually separate from the F# one.
Could you also show on the DU part of it is the cases, the second one is attaching data to the cases. Could you show again on your DSL how it looks? Like if I have a case like green of 10.
Oh, yeah, for sure. Actually, so that code is actually not here. It's in the C#. It's actually in the C# DU types. It's a different project entirely. But I actually deal with that and use pattern matching to do a whole bunch of stuff. So the types are actually fully closed. You can't extend a DU even though it's written in C#. Anything else?
I think you have the last question. The piece which is not obvious to me is like why audience or like what's the relationship? Like do I have to use audience to use this?
Oh, no. So why Orleans? So the most important thing stems back all the way. So there's several pieces to answer that problem, right? The first one is this. When you write an interactive system, the whole idea of the shape-shiftingness of the object and removing the capability and the affordance and decoupling those two, that's kind of a very important property. It's an approach for doing the development that I really like. Now, Another thing I really like is to be able to build applications at scale easily using the same kind of principles, or principles that allow for that kind of affordance and capability decoupling. So because it is easy, we have taken a problem that is interactive in nature and made it an object-oriented problem. And then I've taken the object-oriented paradigm that's espoused by Orleans, and it's just a natural fit to put the two in place. But any other object-oriented system can also be generated in, the language, the DSL is language agnostic, the parser is language agnostic, the code generator is the only thing that generates Orleans. You can quite easily plug in another code generator on the same AST. In fact, what I wanted to do, if I had the time before doing this talk, was to process the AST using a graph mechanism so I could just draw the state machine out. And it's very easy to do that. And basically, it opens out the ability for us to write code that is easy to reason about because we're talking about it at an abstraction level that removes ambiguity about its behavior. And that's really the key piece in this whole thing, is trying to promote and lift and declare the intent in such a way that we can actually reason about it without having to dig through the code. So it's Orleans because Orleans is the most elegant way of actually building that object-oriented, scalable approach. But you can definitely apply it to any other scenario that you want.
If I write my client in F#, will I be able to achieve the same and build such state machines just by using native F# estimated unions without using this extension class of unified?
You kind of need the restricted types because if you don't, you have no way of actually modeling valid transitions. The valid transitions piece, the type safety of the valid transitions piece is kind of the thing. If you look at the state machines out there, all of them effectively I'm in a state, I take a message, I go to another state. There's no way to tell that the set of states that you're going to is a valid set of states. You can only do that by modeling it as a type problem and saying this set is actually a restriction of this set. And that's a very critical difference between this approach and every other approach I've seen so far. Shall we break early? Cool. Thank you so much.